You can study psychology up until your PhD and end up doing very mathematical and computational data science at Google, right? It's too hard of a U-turn. Some would even say it's nuts just because they like bad puns. Well, think again, because Junpeng Lao did just that. Before doing data science at Google, Junpeng was a cognitive psychology researcher at the University of Fribourg, Switzerland. Working in Python, Matlab, and occasionally in R, Junpeng is a prolific open source contributor, particularly to the popular TensorFlow and PyMC3 libraries. He also maintains the PyMC Discourse on his free time, where he amazingly answers all kinds of various and very specific questions. In this episode, he'll tell you what the core characteristics of TensorFlow Probability are, and when you would use TFP instead of another probabilistic programming framework like Stan or PyMC3, for example. He'll also explain why PyMC4 will be based on TensorFlow Probability itself, and what future contributions he has in mind for these two amazing libraries. Finally, Junpeng will share with you his workflow for debugging a model, or just for better understanding new models. This is Learning Bayesian Statistics, Episode 7, recorded November 29, 2019. Welcome to Learning Bayesian Statistics, a fortnightly podcast on Bayesian inference, the methods, the project, and the people who make it possible. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country, and reach a true Bayesian state of mind by visiting learnbayesstats.anvil.app. That's learnbayesstats.anvil.app.
Let me show you how to be a good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations.
What's a Bayesian? It's someone who cares about evidence and doesn't jump to assumptions based on intuitions and prejudice. A Bayesian makes predictions on the best available info and adjusts the probability, cause every belief is provisional. And when I kick a flow, mostly I'm watching eyes wide and maybe...
Junpeng Lao, welcome to Learning Bayesian Statistics.
Thank you. Thank you for having me, Alex. And nice to talk to you in person.
It's a pleasure having you here on the show. Thank you for taking the time. Indeed, it's really nice to talk to you because we talk a lot by Twitter or on the Discourse, but...
Yeah, always by text. It's nice to have like conversations in real time, less latency.
Yeah, exactly. It's always a little more magical with a human interaction. I have tons of questions to ask you. It was quite hard to select my favorites for the show. So I think the best is to start by your background. And actually, if I understood correctly, your background is in psychology, but your day-to-day work is very mathematical and computational. So I'm kind of curious here. How come and what's the story behind that?
Yeah, actually, it's quite an interesting story. At the end of my high school, I was going to university. I was really drawn to the idea like Sigmund Freud and this kind of psychoanalysis. That's why I chose psychology, which turns out is completely different than what I was expecting because it's much more a science approach to kind of like to investigate how human mind works in a very general way. And actually at the time, after 4 years of university, I'm still really much into the social aspect of psychology. Actually, at the time, I was really horrible at statistics. I always make the joke that my statistical teacher is the worst ever. And I hope he didn't listen to this podcast and get mad at me. But then I have an opportunity to do a PhD in Glasgow on more perception or cognitive side of psychology. So my PhD thesis is on how culture affect the ways that we recognize faces. And when I started my PhD, the department is quite computational in a ways that they try to run a lot of simulations. They try to have more better method to conduct study and not do analysis. And I started to drawn to the idea of doing bootstrapping and permutation. And to me, a more natural way to understand statistics, I now kind of like by doing simulations, I can actually see how the number change when you change your assumptions, when you change your models. And from there on, I started to kind of like grow more and more interest of more computation science of research. And from my experience of doing bootstrapping and permutations, I started to have more interest in this kind of Monte Carlo method, and then slowly switched to doing Bayesian statistics because Monte Carlos is unavoidable. You started to learn macro chain Monte Carlos. And at the end of my PhD, I was started to feel like I should have acquired a bit more skill because I was using Matlab and it's a closed environment, and also my personal interest to want to learn a little bit more of like programming. So I started to teach myself Python and Bayesian statistics at the same time. And at the time, kind of like the major package in Python for Bayesian statistics is PyMC3. So I just started to explore, to try to use it very naively because at the time I was learning both Bayesian and Python at the same time. But after some struggling, I finally kind of like get a hand on it. So, and also it slowly moved my profile. I started to do analysis more for my labs and also started to contribute more to, for example, PyMC3 and other statistical package in Python. And that's kind of like how my journey from doing psychology into now being a data scientist.
That's fascinating because actually, if I understood correctly, you really transitioned and learned all the statistics, mathematics, and computational methods you're using today. You started learning them only during your PhD, right?
Yeah, pretty late, yeah. I mean, I have some classes like programming, also statistics and research method, but I guess at the time when I was going through the class, I mean, I'm learning in terms of like, I can do the test, I can pass the test, but I don't think it's like really internalized into how I would analyze data. So it's more like acquiring knowledge and now more in the ways that I can actually apply the knowledge, I guess.
That's really impressive. And also, I guess it's inspiring, I hope, for some of our listeners, because it means that just because you didn't start your undergraduate studies in mathematics and statistics doesn't mean you can't become a data scientist and go more into data science, programming, statistics, and so on.
Yeah, definitely. I think I'm really fortunate because my supervisor is really supportive. So at the time, during my PhD and during my postdoc, I have a lot of time to learn and to explore the idea and to just like simple, like just learning to program because sometimes some supervisor may want you to, just do this analysis quickly. But my supervisor gave me quite a lot of freedom to actually apply the technique that I wanted to and to learn the technique that I wanted to use.
That's really awesome. Congrats on all these learning path that you took. And actually, you have another really characteristic trait that I found in your profile because, well, there is this trait that you didn't start by math and statistics. And the other thing that was striking to me was that you work at Google today, but you did your PhD in Europe and you are still based in Europe. So I'm quite curious because I think you're my first guest who's based in Europe, and actually, except Osvaldo Martin, I think all my guests live in the US. So I'm kind of curious here what compelled you to come to Europe.
I think compel is a little bit of a big word because it's more a consequence of lots of lucky and fortunate events. So at the times that for doing my PhD is because my undergrad supervisor already have collaborations with my PhD supervisor. So it kind of makes sense for me to continue research to go to the UK. And then my PhD supervisor got a position near the end of my PhD. So he moved to Fribourg, Switzerland. And that's why that I kind of follow the whole lab to Europe. So in a way that I didn't make a lot of conscious choice to be in Europe. So in a way I'm extremely lucky. And in terms of joining Google as a data scientist, that's also another very fortunate kind of happy coincidence because I was at the end of my postdoc. So I just started to look at different postings, mostly still within academic, and just like really by chance, I actually haven't even crossed my mind that I should explore more, but I come across the Google career page and I just search for Bayesian, and then I find those postings that it seems to fit quite well of my profile. So I just apply, and lucky enough, I got it. So yeah.
Yeah, that's interesting. There is a kind of random elements in your profile. In a sense, you were bound to study random sampling and so on. Actually, because you already anticipated my next question, because you already told us how you first got introduced to Python and Bayesian methods, I'm curious what was their main asset in your mind, and today, what proportion of the time do you use them?
In my work, I use Python almost exclusively, or at least as much as I can. Usually, the works that we do, we will use SQL language to get in like raw data from the logs. And then most of the time, I will just do all of my processing in Python. And then we would call different libraries, of course. And if there is a need, we might rewrite some of the logic into other language like C++ or Go. But I would say majority of the works that, for example, for data analysis, at least me and my team tend to do it in Python.
And concerning Bayesian methods, what's their main asset in your mind?
Well, I certainly try to apply it whenever I can, but sometimes it might not be necessary because sometimes you can demonstrate an idea easier, either just using frequency statistics or even just use descriptive statistics, because sometimes you have millions of records, and if you just compute the mean or you just plot the data, it's clear enough that it doesn't need additional statistics on top. But there are also cases that I do need to do a little bit more complex modeling. And then I would tend to use whatever method that I find is the most convenient.
Yeah, so basically, like, if you have millions and millions of observations, well, maybe it's not the best use case for Bayes.
Well, yeah, I guess in terms of what kinds of information you want to get from the data, because if you break it down into like grouped it by different cases, there might be a lot of area that you actually need more complex modeling.
Yeah, okay. And actually, how widespread these methods in your line of work? Do you often have to convince people to at least try some Bayes stuff when you think it's relevant to a project? And when you have to convince them, how do you go about it?
That's a really interesting question because actually my team, we have a quite diverse profile. So we have people that used to study physics, used to study engineering, data scientists that used to do mathematics and statistics, of course. So we kind of all come with different perspectives. Me personally, I don't try to force kind of like, oh, everybody should use Bayesian. Although implicitly I was like, yeah, that makes sense for me, but it might not always make sense for other people. So what I try to do is that if I have a problem that I think is showcase the advantage of going about a Bayesian approach. For example, if there's a lot of knowledge or this information that from previous analysis, it would make sense to incorporate that into your model. And I find that Bayesian is just a principal way to make sure that you don't discard any information. So if you already have this information from the prior analysis or from the problem setup, you should always try to incorporate it. And to me, it just makes sense to be in Bayesian. But for other people, it might make sense to, for example, just put in the penalties on the loss functions or using deep learning, but with a specific way of training your model so it takes into account of prior knowledge. So I think in a way that as long as you get your job done, I won't force anybody to be Bayesian. But of course, if people consult me, I will always say, oh, have you tried or have you think about of using a Bayesian model to do this? And yeah, that would be my approach.
That's very interesting because I guess lots of people work in diverse teams as you do. So it's always interesting to know other diverse teams do to speak the same language in the end. And I'd like to turn to TensorFlow Probability now, as you're one of the core developers. And I didn't have anyone from TFP on the show yet, so maybe you can just say what the elevator pitch is for the listeners.
Yeah, definitely. Well, first of all, I think a core developer is overpraised for me. I contribute as much as I can. Yeah, so first, elevator pitch. I think it depends on the audience, right? If it's data scientists, it's a bit difficult because in a way that I think for me, it makes sense because as in Google, we have all the infrastructure is built around TensorFlow. So it just makes sense if you use TensorFlow Probability because it integrates with all our tools really nicely. And if I'm pitching to another data scientist in another field, I guess I would need to know more about what is their application. And I would try to convince them, oh, actually, if you do it this way in TensorFlow Probability, probably it will make your life easier.
Okay. Actually, when would you use TensorFlow Probability instead of other probabilistic programming frameworks? Like we talked a lot on the program about PyMC3, and I had Michael Betancourt the other day, so we talked a lot about Stan too. These are really good frameworks. You contribute also a lot to PyMC3, so I'm curious when you would use one instead of the other.
That's a great question, because I guess at the end of the day is whether you are choosing one or the other depends on a lot of the teams and kind of like the setups you have. I would say that I find you being in a TensorFlow and TensorFlow Probability, this computation environment comes off a lot of nice in the engineering point of view, that when you try to productionize your model, at least Google try to make it quite easy. You can set up this cloud instance on Google Cloud, or you can use Colab straight out of the box with the free Colab instance. So these are kind of like nice things to have. But in terms of, if you think about a little bit kind of like in the longer terms, in terms of like the future, how probabilistic programming language is moving, I think TensorFlow Probability has great advantage that is developed by a dedicated engineering team. I mean, it has some drawback as well. I might come to it later, but at least the main kind of advantage is that all the design is super well thought. For example, I was so amazed in the very beginning when I saw the design for distributions. And there was the time, even before I joined Google, is that distribution come with 3 different kinds of shape. So shape is kind of like these things that I personally love to talk about, because in PyMC3, we used to have so much problem and users struggling with like shape problem, we call it. And TensorFlow Probability has the nice setup that they are divided the shape into 3 different kinds. So you have the event shape. Basically, it means that when you are computing your log probability, which dimension out of the rank of your input it should collapse to. And then it has a batch shape. Basically, is a easy expandable way that for you to multi-batch a program. And then it has a sample shape, basically is for if you repeat the sample from the same distribution, then you have the sample shape. So there are still a lot of cases that has some awkwardness, but at least I think the framework is a great innovations. And here shout out to a previous TL of TensorFlow Probability, Josh Dillon. He came up with this system. It's really much better way for guiding user to think about shape. And that's kind of like the first impression I got from TensorFlow Probability. And subsequently, I guess many of the design have the kind of like usual drawback that it has a bit of complexity, because they try to cover as much ground as possible. But at least whenever they have codes that follow the initial design, or have like well thought codes that actually think of the design, I tend to find that the program also in a ways that a little bit more safe, I would say.
Yeah, that's interesting, this comparison with the other frameworks. And so you touched on it a little already, but I'm wondering, in your mind, what are the core choices you made as a team TFP that made TensorFlow Probability what it is today? If you had to pick the core characteristics of TensorFlow Probability, what would you say they are?
Well, shape is definitely one. And then the other really nice design pattern is the transitional kernel. So when we are trying to think about doing macro chain Monte Carlo, we think of there is an unknown. So all the 3 variables in your models that you want to do inference on. And the transitional kernel in a macro chain Monte Carlo is basically taking a state from the previous iteration and propose a new state. And then if you're doing MH acceptance, you decide to either accept or reject this proposal, and then it goes on. And the transitional kernel is nicely designed in a ways that it fits all the needs, that it takes a previous state and then with some metadata. For example, you want to keep some metadata around just for tuning your transitional kernel, or the kind of like things that you can do diagnosis later on. For example, like divergence in HMC or the acceptance rates in any kinds of macro chain Monte Carlo algorithm. And the transitional kernel is designed in a ways that you can easily subclass the module and then build another transitional kernel on top of it. And it's designed in a ways that it fits the pattern of TF.while loop. Because for doing computation or doing while loop or for loops in TensorFlow, you need to write it with a TF while loop. It takes a long time to get used to, I have to admit. And it reminds me a lot of when I first encountered it in Fiano. It also has the Fiano scan. Basically, this way, not writing our for loop directly like what you would do in Python, but you write operator or operation that when you call it, it does the for loop or the while loop. It's something that it really needs time to get used to. But when you kind of like finally get it, you just really appreciate how simplistic and how nice the design is for transitional kernel. I guess it's a shame that this kind of like nice design pattern is never explicitly laid out like in some blog posts or in some papers, because I think it would be great to advertise a little bit more or why the team choose this kind of design and why is it nice. And in many cases, I think that sometimes even the designer haven't realized how nice it is, because if there's not enough using it to discover what you can do with this kind of pattern, it's difficult to showcase like how great it actually is.
Yeah, plus, this kind of conceptual presentation and I hope understanding is really interesting to have also when you use the package afterwards, because then when you inevitably have some problems building your model, you can better understand the error message you've got and so on. Yeah, it's quite rare to find that, but there is this podcast now to do that.
Yeah,
so.
yeah. Yeah, and just circle back a little bit back to like using TensorFlow Probability. I think it does have a little bit of a steep learning curve because of this nice design. It has a little bit of additional complexity built on top that user need to basically spend time to learn these patterns and get used to it. And which is why PyMC team is trying to build PyMC4 that hopefully do away this complexity so that other users like data scientists don't need to go really deep into the understanding of the implementation, but still have a nice library that they can run reliable, fast inference.
Yeah. That's a very good teasing you're doing right now, because I want to ask you about PyMC for a little later. But first, just to close up on TensorFlow Probability, I'm wondering what are the team's projects for the coming months? What are you guys focusing on, and what are you excited about for the coming months?
Well, first of all, I cannot speak for the team because I'm not in TensorFlow Probability team. For me personally, I have a few areas that I feel really excited about in the context of PyMC4 development. For example, getting the mass matrix adaptation running for NUS and HMC. If just in case our listeners don't know about it, so in no U-turn sampler, which is kind of like this dynamic Hamiltonian Monte Carlo sampler, it's really important that we have a mass matrix which guides how the sample should go along the gradients. It's really important for the efficiency of the algorithm that the mass matrix is kind of approximately to the covariance of your posterior. Of course, if your posterior is completely doesn't look like a Gaussian, then that might hurt you actually. In many of the cases, we find that it's really useful and actually makes your sampler much more efficient. And that's what arguably power Stan and PiMC3 of the fast sampling. So we are trying to replicate this also in PiMC4 and in TensorFlow Probability. And so that's one of the main areas that I'm currently working with. And otherwise, just looking to bring more of the feature from PiMC3 to PiMC4 and also potentially TensorFlow Probability. For example, like sequential Monte Carlos that I'm currently working with. INLA, so integrated nested Laplace approximation, which is a method that I really want to know more about. I also want to bring that into TensorFlow Probability. Also some new methods here and there that I want to try out. So that's more like from my personal side as internal/external contributors point of view.
I guess you won't get bored in the coming month. You've got a lot of projects. That's awesome to hear. Yeah, actually, maybe just for listeners that don't know what SMC is, a sequential Monte Carlo, can you explain that a little bit and what's the difference with other Monte Carlo methods like NUTS?
Yeah, gladly. So sequential Monte Carlo is also known as particle filter. The idea is, in a very rough way, is that you would initialize a group of particles. So you can think of it as states, or you can think of a replica of the state in a macro chain Monte Carlo. Or if you sample many different chains, you can think of it as like a group of points, I guess, to represent the space. Because if you think of macro chain Monte Carlo, at the end, we want to have samples that converge to like a random sample from posterior. So it's a similar idea that what the sequential Monte Carlos wants to do. And there's many different forms because you can use like a filter, which means that you can have states from yesterday, and then today you have new data, and then you just refine all the particles so that it converges to the posterior condition on yesterday's posterior, which is now the prior, and also today's observation. And that's one form of it. And the other form of it is you just use it as any other kinds of macro chain Monte Carlo. The differences is that now you would take all the samples at the last stage as the representation of the space. Kind of nice things of sequential Monte Carlo is that it does not necessarily need a gradient of your likelihood function. So it's also closely related to approximate Bayesian computation, which means that if you have a probabilistic program that you can generate sample, you can use this kind of method, slowly bootstrap yourself, starting with a group of points. And at the end, you hope that collection of points actually quite nicely describe posterior space you are in.
So when would you use SMC instead of nuts, for instance?
I don't know yet, to be honest with you, because I think for now, there's more focus on nuts in general because of Stans and PyMC3. But I personally always feel like there's also a lot of potential in SMC. It's just that we don't have good enough tooling in the previously for people to actually try this kind of method. Because the nature of SMC is that you need a lot of parallel chain. And then you need to be able to select states and mutate the states at each step. And the way of the setup, at least for PyMC3 for sure, in some extent for Stan as well, is that all the parallel chain currently, the number is kind of bounded the core of CPU you have. So when we are trying to do this kind of sampler that you need kind of tens of thousands of chains, it actually have some difficulties because it physically cannot fit that many chains. Of course, it works a little bit differently in real life. For example, in PyMC3, thanks to Osvaldo for maintaining and contributing to the SMC algorithm. But I personally find that a very attractive idea to be done in TensorFlow Probability because now you can draw millions of samples and you can run this kind of batch operations almost with really little overhead. And that means that it virtually makes no differences in terms of computation time when you're sampling 10 chain or you sample 1,000 or 10,000 chain. Of course, there's still overheads, but the overhead is much smaller. So now it means that if you're doing things like sequential Monte Carlo or this kind of replica exchange Monte Carlo, which is already one of the samplers in TensorFlow Probability, it means that you get all the samples for free and they're living kind of like in the memory or at the same time, you can manipulate them much easier. So now, because they are not in isolated process like what NUS is doing in PyMC3, it opens a much larger kind of playing field to implement efficient algorithm. And I think by making this better, we now can be in kind of like the same level field because when people are saying, oh, I run SMC, but it's not as good as NUS, now we have a much more level field to play with. And we can say that, oh, actually, maybe SMC is more suitable for this class of problem. And maybe NUS is more suitable for that class of problem.
Yeah, that's very interesting. If you have several very good samplers at your disposal, you can pick and choose the one most appropriate to your use case, depending on what you want to do. That's interesting. And also for listeners interested in what you talked about, the idea that you can sample thousands or millions of chains with TFP. This idea, I actually talked about that also with Colin Carroll. I think it's in episode 3.1. So if people are interested in that, we talked about that also.
Yeah, I discussed with Collins of like a couple of times on that as well, because it also could open quite a lot of new challenges. Because traditionally, we always quantify the convergence or how good your sample is by using techniques like AHAT or effective sample size, which assuming has this kind of like implicit assumption, I would say, you're running a long chain, like at least 1,000 samples, 2,000 samples. But now suddenly you have the option to just run 100 samples or even 10 samples. And these actually give lots of challenge how to use like old conversion tools like I had, because now the estimation is not as good, but hopefully we can develop something that is more suitable to quantify the convergence for a situation when you're just running a short chain, but running a lot of them.
Yeah. Now that we did some teasing before about PyMC4, I think it's a good time to talk about that, because if I understood correctly, PyMC4 will be based on TensorFlow Probability itself. So it's really interesting, this idea. What's the idea here and how will it change compared to PyMC3?
I guess the main kind of like same consistency across PiMC3 and 4 is that we'll try to make it as this kind of inference button. So paraphrasing from Thomas, it means that users would write down their model as if they would write down it on a piece of paper, or as if they are just copying line by line from an academic paper they're reading. And then they just call one function or click one button to get the samples. So lots of our works is basically to have a design that kind of fits this ultimate goal. There's still some challenges because PiMC3 and PiMC4 are built in completely different backends. There are some of the patterns that we are almost really relied on in PiMC3. Now we cannot really replicate it in PiMC4. So we actually need to come up with new design ideas and new implementation to hopefully capture the magic of PiMC3.
And how is the shape handling looking in PiMC4?
Still difficult, but I would say better. At least now we have more control of how the shape is formatted in the backend. So it's more just to have more cases to handle all the edges. And yeah.
Yeah. And I think it's Luciano Paz who handles all these shape issues in PiMC3, right?
Yeah, he did a lot of contribution of shape handling, and it's a great effort, and we are extremely thankful of his thought put into the redesign, and hopefully many of the design can also upstream now to PiMC4, because I guess we all learn over the ways that what might be a better approach to write this kind of package.
Yeah, definitely. So thank you very much, Luciano, for all your shape-related work. Just to summarize for listeners, what you said about PyMC4 was that the idea is to have something on top of TensorFlow Probability with less boilerplate code that allows users to specify their models at a more conceptual level and then to hit on the inference button. Right.
Well, that's the goal we aspire to.
Yeah, that sounds really promising. I can't wait to see the results. Yeah. Yeah, and I see you guys do a lot of work around that. So it's always very interesting to follow it, notably on GitHub. I'll advise all the listeners to take a look at that repo because it's very interesting. Now, to close up the show, I'd like to focus on your teaching experience, because last year you gave a very interesting tutorial on how to diagnose divergences in models. And I'll put the link in the show notes, of course. But what's the short version here? What's your workflow when diagnosing a model with divergences?
Well, first of all, I would do all those usual blocks. That's kind of like always first step when you have divergence, just to get an understanding of where the divergence is. And sometimes they might not make sense, but usually when you see a lot of them, that's always extremely bad size. In most of the case, I guess the divergence is always from kind of careless or not putting enough thought or priors, because if you have a prior that is too diverged in a ways, of course, it depends on what kind of model you're fitting, and there's a lot of great advice from the Stan. I think it's a GitHub wiki page advising you what is the good prior in principle to choose. So yeah, that's kind of like, it's a little bit difficult to explain it really coherently because many cases depending on the models. So sometimes if you see that people are complaining, oh, I have this mixed effect models and I have huge divergence. And if you look at their model, you see that they just have lots of half-Cauchy prior on the sigma of downstream to plug into a normal distribution, then you already feel that oh, this prior is actually really difficult because it has put a lot of weights in the tail area. So have you tried to just use a bit more informative priors? Or if you are actually modeling the random effects, maybe it's good that in the very beginning, you just fix the random error there and just basically cut down the complexity of your model. And when you're certain the simple version of your model works, and then that's the times of adding more complexity to the model. That's kind of my general approach of how to debug these models.
So like if your ultimate goal is to have hierarchical model, which is a very good goal, I'd say, then if it's a difficult model, maybe just start by a non-hierarchical version of the model, which means that your mean and standard deviation, for instance, are fixed. You see if the model can sample, if the predictors have some value. And then when all that is working, you can add the hierarchical layers.
Yeah, definitely. So just as an example, for example, if you're fitting a linear regression, if you use standard package and just look at the coefficient, it makes almost no differences. The sigma of the likelihood of the observations being a fixed number or being a free parameter. Because at least for many of the statistical tools that out of the box usually use either this kind of maximum likelihood estimation, you just don't care about the sigma terms in the likelihood function. Well, assuming your observation is normal, of course. These are kind of the heuristic in a ways that it's fine that you want to add complexity into your model to capture more information that you actually need. But it's always a good practice from my point of view is to start simple. And when things don't work, just try to eliminate those complexity first. Yeah.
Yeah, very interesting. I didn't record any episode yet dedicated to multi-level models, but I want to do that. And I'm teasing a little here, but normally I'll have Thomas Vicky on the show to specifically speak about hierarchical or multi-level models.
Yeah, looking forward. I mean, at the end of the day, I would say hierarchical linear model powers, I would say 95% of our work. So
yeah, exactly. Yeah. Plus the Bayesian framework makes it a lot more intuitive to build hierarchical models and at least more easy to understand on a philosophical level.
Yeah, definitely. And also I would say that we even push a bit further that it's only because now we have these great Bayesian tools like Stans and PyMC3, we can actually fit this complex hierarchical model. Because before, these are extremely difficult to do and really slow to do. And we many times would have quite biased results just because we don't have good enough tool to fit these models.
Yeah, that's true. And in any case, even with awesome tools like Stan or PyMC, you have to be very, very careful about your chains and also, as you said, your priors. And actually, that gives me a nice transition to my next question, because I often see on the PyMC Discourse a lot of questions of people that have divergent chains. And in the end, they discover that it's because their priors were not regularizing enough. And when you do some prior predictive checks, then you can sample your model and you understand what your priors are. So I'm curious, because you're actually the maintainer of this PyMC Discourse. And well, first, I have to say, I'm always amazed at how you manage to answer so many questions on various and complex topics. It's very impressive because often you have some researchers coming with a very, very specific question on his topic, and you often can give an answer.
Thank you. It's a learning experience. And I certainly make a lot of mistakes as well. So don't look too deep into it.
I mean, it's impressive. And that's also the spirit of this podcast. You have to make mistakes to grow your skills. So I'm wondering, from this experience, are there classic recipes that you can give people to debug their models or maybe think better about the models?
It divides the question in a way into two classes. I mean, one class is problem kind of more computational. Basically, it means that you have a model, you think that you write correctly, but it just doesn't sample or it gives nonsense result. And usually I would say more than 50% of this problem for me or for the PiMC3 maintainer is a bit obvious to see. And we are actually over the years, thanks to the feedback of user, build a lot of tools that help people to diagnose this. For example, we used to always advise people to just write a for loop, go through all the three parameters in the models and print out the default values and print out the log probability if you evaluate on these default values. And sometimes you see that just by accident, some of these nodes will give out nuns, and it could be various reasons. For example, even the input data contains nuns or the user used the wrong priors. So this kind of like a way to diagnose this. We listen to user and try to add more helper functions to diagnose this. Otherwise, lots of shape issues, of course, because the shape handling was, let me say, is less than perfect in PiMC3. So a lot of the time, it's just to print out the three parameters test values. So which is a way to see the caches or the default value of the random variable and try to plug that in NumPy into the next computation, kind of like just to see how the next step output looks like. And that's, I would say, this approach can solve quite a lot of problem already. And then the other class of problem is much more difficult because they involve kind of domain knowledge. They are user quoting from a paper or just asking, how do I implement this from this paper? Then those questions would take much longer time to answer and to help.
Yeah, that's true. And I actually asked a question like that on the discourse.
Oh, we welcome all kinds of discussion. And actually, over the years, I think we grow quite a nice community. People like you, for example, thanks a lot of answering other users' questions lately. We hope that we foster a healthy community. So actually, everybody help each other, right? So that's kind of like, I always think that open source development is more about the community than the actual software you write. Because you can write a perfect software, but it's maybe nobody use it, and it's kind of like a waste, right?
That's true. The community is very welcoming, and as you say, I'm trying to answer some questions. Of course, I can't answer as many as you are for now, but I'm trying.
I don't answer a lot right now, so I bet you answer much more than me.
I think that's not the same type of questions I answer. Mine are easier to answer. But yeah, just to wrap up on that, yeah, that's true that the community on that is very welcoming, and that's really something that goes into PyMC's calm, I'd say. Okay, Junpeng, so I don't want to take too much of your time. So, of course, I still have many more questions, but I'm gonna ask you two final questions. I ask every guest at the end of the show. The first one is, if you had unlimited time and resources, which problem would you try to solve?
Yeah, it's funny that because I listened to all your previous podcasts, I know this question is coming. I still don't have think of a perfect answer in a way that I'm happy about. I guess really enough, I think I might probably devote those resources into solving fusion technologies, because I think all these renewable energies nowadays, it doesn't seem to be effective enough. And I do think nuclear energy should be a focal point to solving this energy and environment crisis that we're having. So I know that it seems like there's a research going on, but it's never going anywhere. But I do hope that more people are devoted their career and government devoting resource to this area.
Yeah, that's an interesting answer. I didn't have that one yet. If you do that, then come do some research in France. The government is pretty active on that front. Okay, and the second question is, if you could have dinner with any great scientific mind, dead, alive, or fictional, who would it be?
I think this one I have a better answer, because I think I would want to have dinner with Euler, that is also from Swiss. And he's actually born in Basel. And Basel is a beautiful city. So if all of our listeners out there, if you have a chance to visit Switzerland and visit Zurich, I highly recommend it. And yeah, I would have dinner with Euler because he's such a great mathematical mind and basically pioneer of almost all the mathematical fields that currently exist. And I guess he's a few hundred 100 years ago. So many of the math that I can actually discuss, I might be able to discuss with him, because all the new mathematics, I probably won't be at that level to have a good conversation. So yeah.
Yeah, that's a nice choice. I didn't have that one yet. Also, so very interesting answers yet. And that's true. That must be fascinating to have dinner with him. Plus, you could discover what they were eating at that time.
Probably quite a lot of cheese.
yeah, that's true. Well, Junpeng, thank you very much.
Thank you very much, Alice.
It was super interesting talking to you. I am, again, very grateful for the work you do at PyMC and TensorFlow Probability. And I think listeners now have a better idea of what these libraries are and how they will evolve in the coming month. And I hope also we helped some people with their divergent models. So thank you again, Junpeng, for taking the time and being on this show.
Thank you. Bye.
This has been another episode of Learning Bayesian Statistics. Be sure to rate, review, and subscribe to the show on your favorite podcatcher, and visit learnbayesstats.envol.app for more resources based on today's topics, as well as access to more episodes that will help you reach true Bayesian state of mind. That's learnbayesstats.envol.app. Our theme music is Good Bayesian by Baba Brinkman, with MC Lars and Mega Ran. Check out his awesome work at bababrinkman.com. I'm your host, Alex Endora. You can follow me on Twitter at Alex_Endora, like the country. Thanks so much for listening. You're truly a
good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. Let me show you how to be a good Bayesian. Change calculations after taking fresh data in. Those predictions that your brain is making, let's get them on a solid foundation.